Welcome everyone to the course, A Roadmap for Sustainability and Decarbonization of Buildings. The role of exploit for Inamat. This course begins by introducing the concept of green building, a fundamental approach shaping the future of sustainable construction across Europe and beyond. Building on this framework, we will then present the innovative materials and solutions developed and demonstrated within the Exploit for Inamat project. In this session, we'll look at what building green really means in practice and why it matters so much today. The building sector is one of the largest consumers of energy and resources worldwide. Buildings today are responsible for nearly 37% of global greenhouse gas emissions, combining both operational and embodied energy. Operational energy refers to the electricity and heat used during a building's life, lighting, HVAC, appliances. Embodied energy comes from materials, extraction, production, transport, and construction processes. Achieving carbon neutrality by 2050, as outlined in the European Green Deal, requires deep transformation in both areas. How we design and what we build with. That's where the green building paradigm comes in. So what do we mean when we talk about building green? First, we're talking about structures that are designed to minimize their ecological footprint across their entire life cycle, from the extraction of raw materials, through manufacturing and transport, to construction, operation, renovation and end of life. Second, building green is holistic. It balances environmental stewardship, economic viability and social responsibility. A building that is super efficient but unhealthy to occupy is not green. A building that is low carbon but unaffordable for most people is also not delivering on the full agenda. Third, building green is directly linked to global challenges, climate change, resource depletion, and social inequality. The three main pillars of a green building are therefore environmental sustainability, economic sustainability, and social sustainability. The challenge is to balance all three pillars. Historically, green building began with passive design strategies, better insulation, orientation, daylighting. Then came performance certification systems such as LEED, BREEAM, and DGNB, which standardized sustainability assessment. Today, we've entered a new era, the digital and adaptive phase. Using advanced simulation tools, data analytics, and smart materials, we can predict and optimize performance long before construction begins. This evolution reflects a shift from design intent to measured performance, and that's where innovation in materials plays a crucial role. Let's understand the relevance of green buildings. Think of a building not as a static object, but as an energy system. Every wall, window, and floor mediates the flow of heat and light, storing, transmitting, and releasing energy. The envelope acts like a dynamic interface between the indoor and outdoor environment. By optimizing its thermal and optical behavior, we can significantly reduce energy demand while improving comfort and resilience. That's why the integration of materials science, physics, and digital modeling has become essential for sustainable design. Green buildings reduce emissions in several ways, through high-performance envelopes that cut heating and cooling loads, through passive solar design and natural ventilation, through efficient glazing and shading, and by incorporating renewables like solar PV, small wind turbines, and geothermal systems. One key point is the reduction of energy demand by using smart management systems, sensors, natural ventilation, and daylighting to decrease reliance on artificial cooling and lighting. Another fundamental point is water conservation. Water use is more efficient through rainwater harvesting, greywater recycling, and efficient fixtures to reduce demand on municipal systems and increase resilience, especially in regions facing water scarcity. Other important points are to ensure indoor comfort through advanced ventilation systems, high-performance thermal and acoustic insulation, and access to green spaces. To make this more concrete, let's look briefly at some flagship projects. First, One Central Park in Sydney. This mixed-use complex combines vertical gardens with on-site solar panels and a heliostat system that reflects sunlight into shaded areas. The green facades help to reduce heat gain, improve air quality, and provide a strong visual identity, while the renewable energy systems reduce dependency on the grid. Second, Bosco Verticale in Milan, the vertical forest. 2 residential towers carry thousands of trees and shrubs, acting as a piece of urban ecosystem infrastructure. These facades sequester CO, produce oxygen, reduce the urban heat island effect, and provide natural shading and insulation. The project also shows that biodiversity and high-density urban living can coexist when design is thoughtful. Third, the Edge in Amsterdam. Often described as one of the world's smartest and greenest office buildings, it combines very efficient envelopes, more than 4,000 square meters of PV, and a sophisticated smart building system that adapts lighting, heating, and cooling to occupancy and user preferences. This kind of project shows how digitalization and sustainability can support each other. Finally, the Crystal in London is a highly efficient urban building that integrates rainwater harvesting, solar power, and smart energy management. It functions as a demonstrator of what a low-impact urban building can look like in practice. What are the key elements of a green building? Energy and water efficiency. On the energy side, we differentiate between passive and active strategies. Passive strategies include building orientation, compact building forms, effective insulation, high-performance glazing, minimizing thermal bridges, and using thermal mass to smooth out temperature swings. Active strategies complement this with efficient systems, heat pumps, high-efficiency boilers where needed, mechanical ventilation with heat recovery, efficient chillers, and LED lighting. Smart controls and zoning ensure we only heat, cool or light spaces that are occupied and only to the level required. On water, we apply the same logic, reduce demand first, then reuse and recycle. Low-flow fixtures reduce baseline consumption, rainwater harvesting and grey water reuse reduce dependence on potable water, and smart irrigation ensures that any landscaping is maintained with minimal water waste. The next key elements are sustainable materials and indoor environmental quality. For materials, we look at embodied energy and carbon, recyclability, toxicity, and durability. Low embodied energy materials, such as certain bio-based products, recycled metals, and optimized concrete mixes, help to reduce the upfront climate impact. Recyclable and modular components support the circular economy, while durable and easy-to-maintain systems reduce the need for frequent replacement. Indoor environmental quality is about how people actually experience the building. That involves air quality, lighting, acoustic comfort, and thermal comfort. Getting these aspects right is crucial because they directly connect the environmental and social pillars. The same measures that reduce energy use, like better envelopes, can also improve comfort and health. I want to stress here the importance of materials, as they define how a building performs. Materials carry the DNA of a building, shaping its essential characteristics and determining how it behaves. They influence heat transfer, storage capacity, light transmittance, and long-term durability. In the context of green buildings, materials have evolved from passive barriers to active regulators, capable of responding to both climate conditions and user needs. As such, they are critical agents in achieving sustainability objectives and meeting green building standards. Within our research framework, materials are engineered to reduce thermal losses, store and release heat efficiently, and enhance indoor environmental quality. These are precisely the challenges addressed by the innovative prototypes developed in the pilot lines of the Exploit for Inamat project. Here are some interesting case studies. First, the Edge, in Amsterdam, is called the smartest office building in the world. The building adopts an energy-positive design, combining over 4,000 square meters of solar panels with an efficient thermal storage system to generate and manage surplus energy throughout the year. Smart AI-driven technologies optimize temperature, lighting, air quality, and occupancy, while smart meters help occupants monitor and reduce energy use. Sustainable materials such as reclaimed steel and timber are used alongside low-impact interior furnishings, and strong attention is given to health and well-being through advanced air filtration, natural daylight, and ergonomic workspaces. Although initial investment costs were high, these are offset by long-term energy savings, tax incentives, and green funding, with smart systems adapted to Amsterdam's climate ensuring efficient heating and cooling. Next is the famous Bosco Verticale, in Milano, famous for integrating nature into its architectural design. the two residential towers incorporate extensive green facades with thousands of trees, shrubs, and plants, which improve air quality by absorbing CO and producing oxygen while providing natural cooling in summer and insulation in winter. This vegetation reduces reliance on mechanical cooling, enhances overall energy efficiency, and creates habitats for birds and beneficial insects, supporting urban biodiversity and ecosystem regeneration. Although the system requires continuous maintenance, including pruning, pest control, and irrigation, this is managed through automated irrigation and specialized horticultural expertise. While the initial investment was high, the project delivers long-term environmental and economic benefits, including increased property value driven by its iconic design and strong sustainability performance. But what is the role of technology in green buildings? Technology is a key enabler of green buildings, and this set of slides focuses on BIM and IoT. Technology plays a key role in enhancing sustainability, energy efficiency, and occupant comfort in buildings, with growing demand for eco-friendly construction driving continuous innovation. Digital tools such as building information modeling support optimized design choices, while Internet of Things technologies enable real-time monitoring and more efficient energy use through smart sensors. The integration of renewable energy solutions such as solar, wind, and geothermal systems support the development of more self-sustaining buildings. Building information modeling, BIM, is more than 3D modeling. It provides a digital twin of the building that can be used to simulate energy performance, daylight levels, thermal bridges, and even life cycle impacts of different material choices. You can test what-if scenarios in the computer before you build in the real world. It also helps reduce waste through more accurate quantity takeoffs and clash detection between structural, MEP, and architectural elements. This digital twin approach offers a powerful way to connect building design with real-world performance. By combining building information modeling, BIM, and building energy modeling, BM, we can capture both the geometric and functional aspects of a building. BIM provides a detailed digital representation of the building's geometry, materials, and components, supporting design coordination and documentation. BEM, on the other hand, focuses on simulating the building's energy behavior, daylight, airflow, and thermal comfort. Using both together allows us to create virtual prototypes that are both highly accurate in form and performance. Once the building is completed, monitored data is used to refine and calibrate these models, confirming how materials and systems actually perform. This approach ensures that sustainability goals are not just theoretical. They are measurable, verifiable, and truly reflective of real performance. IoT and smart systems bring a similar intelligence into operation. Sensors measure temperature, occupancy, air quality, humidity, and energy use in real time. Smart thermostats and controls learn patterns and adjust systems automatically. Data analytics identifies inefficiencies and supports predictive maintenance, so we fix problems before they become failures. The result is a building that continuously tunes itself to be both efficient and comfortable. When you combine BIM with IoT, linking design models to operational data, you open the door to digital twins that are updated throughout the life of the building, supporting optimization, refurbishment strategies, and long-term asset management. Technology alone doesn't deliver green buildings, we also need enabling policies, financial tools, and market demand. At the policy level, international frameworks such as the Paris Agreement and the UN Sustainable Development Goals push countries to reduce emissions and create sustainable cities. At EU level, instruments like the Green Deal, the Energy Performance of Buildings Directive, and the Taxonomy for Sustainable Finance increasingly favor high-performance, low-carbon buildings. On the financial side, we see many incentives, tax credits, grants, preferential loans, and growing use of green bonds. Case studies like the retrofit of the Empire State Building in New York illustrate how energy upgrades can reduce energy use by nearly 40% and generate millions in annual savings while increasing asset value. Then there's market and society. Demand for green buildings is rising because tenants, investors, and citizens are more aware of environmental issues and health benefits. Certification systems like LEED, BREEAM, WELL and EDGE have become part of the market language. They signal performance and help differentiate assets. At the same time, community engagement and social equity initiatives, like green schools and affordable green housing programs, ensure that the benefits of sustainable construction reach a broader part of society, not just premium segments. This section zooms in on certifications and standards, which translate general sustainability objectives into concrete criteria. BREEAM, developed in the UK, is one of the oldest and most widely used systems. It assesses buildings across categories such as energy, health and well-being, land use and ecology, materials, and water. It encourages holistic improvements and provides a structured benchmark for performance. WELL Building Standard focuses specifically on health and well-being, air and water quality, nourishment, light, movement, comfort, and mental health. It's increasingly used by employers who want to support employee well-being and attract talent. EDGE, developed by IFC, is designed as a more streamlined, cost-effective certification for emerging markets. Buildings must achieve at least 20% savings in energy, water, and embodied energy in materials compared to a baseline. Its simplicity and online tools make it practical for many projects. Behind these schemes we have a whole standardization ecosystem. ISO standards like ISO 21930 for life cycle assessment of construction products, European standards such as EN 15804 for environmental product declarations, and EU frameworks like Levels. Aligning ISO Centre national standards is crucial to reduce fragmentation, support cross-border investments and move collectively towards climate-neutral buildings by 2050. A special focus of this course is on Open Innovation Test Beds, or OITBs. These are collaborative platforms that provide testing facilities, pilot production lines, and regulatory support to help new green materials and technologies reach the market. Open Innovation Test Beds offer testing and validation of material properties, energy performance and environmental impacts under realistic conditions. Pilot production facilities to bridge the gap between lab prototypes and industrial-scale manufacturing. Collaboration networks that bring together universities, research institutes, SMEs, large companies and public authorities. Regulatory and certification support to navigate schemes like LEED, BREEAM, Passive House, and EU taxonomy. Market integration, connecting innovators with investors and construction firms. Open Innovation Test Beds help reduce investment uncertainty around emerging technologies by bridging the gap between research and industrial adoption. They also support manufacturers and innovators in meeting green regulatory requirements and standards, making it easier to bring sustainable solutions to the market with greater confidence. They are particularly important for high-impact innovations such as low-carbon concretes, bio-based insulation materials, phase change materials for thermal regulation, or advanced glazing and PV systems. Before these solutions can be widely used in buildings, they must prove durability, safety, code compliance, and cost-effectiveness. Open Innovation Test Beds de-risk this process and accelerate adoption. Finally, OITBs support the circular economy by facilitating advanced energy technologies, innovative building materials and digital construction methods that are transforming sustainable construction by improving energy efficiency, reducing resource use and strengthening resilience. In short, if we want the kind of innovations we just discussed to scale up, we need ecosystems like OITBs that connect research, industry and regulation. I wanted to spend a few words about the Exploit for INAMAT project. The Exploit for INAMAT project brings together research institutions and industry partners across Europe to develop and validate new generations of sustainable construction materials. Each pilot line focuses on a specific innovation pathway, from thermal insulating mortars to adaptive glazing and advanced coatings. Together, they form a coordinated strategy to move these materials from laboratory development to real-world demonstration. A key component of the project is linking digital modeling with in situ validation. Through BIM and energy simulation, expected performance can be predicted, while monitored data from real buildings confirms how each prototype behaves under actual climatic and operational conditions. This combined approach ensures that every material innovation is assessed not only in theory, but also in practice, providing a clear path toward reliable, market-ready solutions for high-performance buildings. Validation combines multi-scale simulation, laboratory characterization, and experimental monitoring. At the microscale, modeling examines heat conduction, thermal storage, and moisture transport within each material layer. Laboratory characterization provides precise measurements of conductivity, specific heat, density, permeability, and any phase change or hygroscopic behavior, ensuring that numerical models accurately reflect the true performance of the materials. Building-scale simulations translate material properties into overall energy performance and occupant comfort under realistic operating conditions. Field measurements of temperature, heat flux, and humidity close the loop, allowing us to directly compare predicted trends with actual building behavior. This multi-layered validation framework turns innovation into evidence-based performance. By continuously iterating between laboratory tests, microscale modeling, and in-situ observations, we refine our assumptions, reduce uncertainty, and capture seasonal as well as dynamic behavior. The future of green building will be defined by integration between digital intelligence, adaptive materials, and circular design. Buildings will learn from their environment, optimizing their behavior automatically. Materials will become smarter, lighter, and more recyclable. And most importantly, sustainability will no longer be an optional feature, it will be the foundation of every design decision. As we close this introduction, let's remember the words of Jan Arthurs Bertrand. We must learn to live more economically, to place limits on our needs and desires, in order to respect the constraints of the planet. Even small choices in how we design and use buildings can make a big difference. Sustainability starts with awareness, and together, we can build a future that respects both people and the planet. Now, we will present a holistic portfolio of innovative materials and technologies designed to support next-generation green buildings. Across the structural and facade systems, in the framework of Exploit for Inermat project, we examine a range of lightweight solutions, lightweight concretes, mortars, cement-free materials, and 3D printed components that significantly reduce material use, embodied carbon, and construction waste. We also integrate passive energy strategies such as phase change materials, solar reflective paints, and smart window films that dynamically manage heat and daylight. These materials reduce operational energy demand while enhancing comfort. Circularity is strengthened through the use of agricultural residues and construction and demolition waste. Finally, private systems bring renewable energy generation into the building envelope, complementing the passive technologies. Together, these solutions form a comprehensive approach to sustainable construction, addressing embodied carbon, operational energy, circularity, and indoor environmental quality. Let's start with the concrete. In order to meet the new challenges facing the construction industry, such as radically reducing mass and greenhouse gas emissions, it is necessary to use building materials appropriately. The avoidance of waste and the maximization of the recyclability of building components can be achieved with great leverage, particularly in the construction industry. Functionally graded concrete, developed at the Institute for Lightweight Structures and Conceptual Design, ILEK, enables mass savings through the optimization of the interior of components. Functionally graded concrete can be achieved through two sets of measures, micrograding and mesograding. The aim of micrograding is to achieve a continuous grading of the two mixtures by simultaneously dry spraying two different concrete mixtures, one made of normal concrete and one mixed with lightweight concrete aggregates or air-in-training agents, in order to obtain a continuous mass and stiffness gradient corresponding to the subsequent load situation of the component. Reducing the demand for concrete at the construction level by optimizing structures internally is achieved by topology optimization and various continuously distributed concrete mixtures. In addition, further principles aim to homogenize internal stress conditions through the continuous gradation of material properties such as strength and density. Mesogradation, on the other hand, is based on the principle of hollow core slabs. Conventional hollow core slabs are reinforced concrete slabs with internal hollow geometries. These enable savings in concrete volume through displacement bodies made of plastics. A distinction of FGC from conventional hollow core slabs is made by avoiding the use of third materials such as plastic, in addition to concrete and steel, for the production of cavities inside the component. The production of mineral hollow bodies from mortars, concepts for their spatial placement, and for securing their position during assembly and concreting in was described by ILEK previously. Further focus lies on developing the most continuous arrangement of mineral hollow cores possible and varying the hollow core diameters in order to achieve a distribution optimized to the internal stress state of the component. In recent years, a CAM framework implemented in Rhino or Grasshopper with Caramba 3D. It is structured in two parts, the CAD-to-CAM engineering part of achieving layouts of mineral hollow bodies for FGC, on the one hand, and on the other hand, a CAD-to-CAM interface taking into account a simplified and upscaled construction technique by bundling mineral hollow bodies. It enables an integrated digital workflow that tightly couples design, analysis, and fabrication. Within the parametric modeling environment, rapid structural feedback is provided during the design process, allowing geometrical and topological variations to be evaluated efficiently. The structural assessment is based on the assumption of linear elastic material behavior, which is well suited for early-stage design exploration and comparative studies. In addition, the framework extends to CAM-related tasks by incorporating algorithms for the clustering of mineral hollow spheres, facilitating efficient robotic or automated picking and placing strategies. This holistic approach supports informed design decisions while ensuring a smooth transition from digital design to structural evaluation and fabrication planning. The CAD-to-CAM engineering framework integrates rapid structural feedback directly into the design process while consistently accounting for linear elastic material behavior. It has been validated against established reference cases for solid concrete beams and slabs, demonstrating reliable predictive capability within this domain. Building on this validation, the approach is transferable to mesograded slab systems through the application of empirically validated reduction factors, C formulas, enabling an efficient and robust extension of the method to structurally differentiated concrete elements. Pictures show the application of the tool to a slab of constant geometry and loading. The differing boundary conditions of the supports, none, free edge, hinged, and clamped, significantly alter the load transfer and cause different hollow body arrangements to be produced by the tool. Within the CAD-to-CAM manufacturing framework developed in Rhino Grasshopper 3D, dedicated algorithms are implemented for the clustering of mineral hollow spheres to enable efficient automated picking and placing processes. The spheres are systematically categorized into regular clusters, irregular clusters that require local cuts or geometric modifications, linear arrangements, and residual single spheres that cannot be assigned to larger groups. This classification supports process-aware design by aligning geometric organization with fabrication and handling constraints. In addition, the framework provides a dedicated interface for exporting the generated geometries in production-ready formats, ensuring a seamless transfer from parametric design to manufacturing and assembly workflows. Now the placement process of the manufacturing interface is showcased. On the left, the candidate configurations of mineral hollow bodies are shown, organized according to a defined hierarchy. Based on these configurations, the placement algorithm is applied to an exemplary laying zone to evaluate feasible arrangements and handling strategies. Finally, the complete slab geometry is extracted for the given demo building at USTAT, demonstrating the applicability of the workflow at the scale of a full structural element. In parallel, interdisciplinary methods for the integration of recyclates were investigated. Based on these efforts, a model-based life cycle assessment (LCA) tool was developed and validated. Applied to the current demo project at USTAT, the analysis indicates a reduction of approximately 30% in co-equivalent emissions, highlighting the significant environmental potential of the proposed material and design strategies. Another material produced during exploit for Inomat was bioconcrete. Bioconcrete is conventionally produced using fixed formwork, where sand is compacted into standard cubes or cylinders, allowing uniform and controlled compaction. This approach restricts geometry to simple forms. In contrast, 3D printing removes the need for standard formwork and enables the fabrication of complex geometries, expanding the range of architectural, engineering, and construction applications for bioconcrete. What is bioconcrete? Bioconcrete is a material where sand is bound together using bacteria instead of cement. Sporosarcina pastörii bacteria produce an enzyme called urease. Urease breaks urea into ammonia and carbon dioxide. The ammonia raises the pH of the surrounding water. This chemical change creates carbonate ions. When calcium chloride is added, the carbonate ions react with calcium. This reaction forms calcium carbonate. Calcium carbonate crystallizes between sand grains. These crystals bind the sand together, forming bioconcrete. On the right is the conventional production method. Sand is mixed with bacteria and placed in a mold. A piston vibrator with an attached plate compacts the material evenly. The system is then sealed. Urea and calcium chloride are introduced to flood the sand. This treatment is repeated multiple times over 2 to 3 days. During this period, calcium carbonate forms and binds the sand. The result is a solid sand block, known as bioconcrete. This method only produces fixed, standard geometric shapes. Shape complexity is restricted by molds and compaction tools. To overcome this limitation, we developed a 3D printing method for bioconcrete at Exploit for Inomat. 3D printing enables complex, customized geometries. This allows bioconcrete to be applied to a wider range of architectural and engineering problems. Layer-by-layer 3D printing process of bioconcrete. In Picture 1, a sand layer has already been deposited, compacted, and printed. This layer is then lowered. In Picture 2, a new layer of loose sand is applied on top. The sand is compressed using a flat plate. A piston vibrator is attached to this plate to ensure uniform compaction. In Picture 4, the result is a flat, dense surface. This surface becomes the base for the next printed layer. In Picture 5, the new layer is printed according to the predefined G-code. This process is repeated layer by layer until the full geometry is complete. After all layers are printed, the system is sealed. Urea and calcium chloride are introduced to flood the structure. The reaction proceeds for 2 to 3 days. During this time, calcium carbonate forms and binds the sand layers together. The final result is a solid, 3D printed bioconcrete structure. After 3 days, the formwork is opened. The printed elements are fully solidified. Different geometries are visible, bound together through microbially induced calcium carbonate precipitation, MICP. In each image, the bottom left shows the G-code pathway. This illustrates how the printing path was planned. The final image shows the corresponding 3D printed bioconcrete geometry produced from that path. The process was then scaled up to produce larger building components. A print volume of 500 by 500 by 200 mm cubed was selected. This allows the fabrication of facade panels with an area of up to 1 square meter. The large-scale 3D printer has a total size of 4 m in length, 1 m in width, and 1.3 m in height. The leftmost section contains the compaction plate. This plate is equipped with a piston vibrator to ensure uniform sand densification. The section to its right is the 3D printing area. Here, the sand layers are deposited and printed according to the planned geometry. Once printing is complete, the system is sealed. And the same process as in the small system, urea and calcium chloride are pumped into the system and left to react for 2 to 3 days. After this curing period, the formwork is opened and washed. Uncemented sand is recovered and reused for subsequent printing cycles. The cemented bioconcrete component is then ready for application. The main goals and challenges that we wanted to focus on while scaling up the 3D printer. Detailed process description. The system includes a Z-axis that moves vertically. After a layer of sand is applied and printed, the entire build platform is lowered. A roller with an integrated sand holder moves over the empty build area. This mechanism deposits a new, uniform layer of sand on top of the previous layer. Any remaining sand in the holder is released into a collection container. The compaction system then moves forward. A piston vibrator compacts the sand layer, creating a dense and level surface. This surface is prepared for printing the next layer. The X and Y axes are controlled by the control board. Their movement defines the printing path. The valve supplying the bacterial solution is actuated in sync with this motion. This ensures a controlled and precise deposition of bacteria across the surface. The empty sand container is returned to its original position. It is then refilled with sand, preparing the system for the next layer cycle. These are the characteristics of the large-scale 3D printer.
Here are a few pictures of the built 3D printer with a video at the end which shows the workability of the 3D printer.
The construction sector is rapidly evolving as we move toward buildings that are not only energy efficient but also resilient, comfortable, and environmentally responsible. At the core of this transformation is the building envelope, and particularly the materials we select to design and upgrade it. In this context, two lightweight insulating mortars, one for interior and one for exterior application, have been developed. Both materials offer reduced density and improved thermal performance, while the internal mortar additionally incorporates phase change materials for enhanced thermal energy storage. To achieve these functionalities, the National Technical University of Athens developed two intermediate materials, a closed structure expanded perlite and a hybrid perlite. These intermediates provide added value and improved performance to the final mortar formulations. This section of the course focuses on outlining the workflows used for the development, optimization, and validation of these added-value insulating mortars. Mortars have traditionally served as simple finishing layers, primarily for protection and aesthetics. However, as buildings progress toward higher energy performance, their role is rapidly evolving. Today, mortars are expected to contribute to insulation, enhance indoor comfort, and support more sustainable construction practices. Conventional mortars, however, remain heavy, thermally inefficient, and incapable of regulating temperature. In contrast, our two innovative mortars, a lightweight external formulation and an internal PCM-enhanced one, deliver improved thermal performance, greater indoor comfort, and a clear step forward for green, energy-efficient buildings. To enhance the performance of the developed mortars, a closed structure expanded perlite was produced through a controlled, purpose-oriented manufacturing process. The raw perlite is first crushed, sieved, and then expanded into a vertical electric furnace equipped with 6 pairs of independently controlled heating resistances. This design ensures precise management of temperature, particle movement, and residence time throughout the chamber. By applying a carefully tuned thermal treatment and optimizing the feed characteristics, it is possible to engineer fillers with targeted size, porosity, sphericity, and density. The resulting closed structure perlite achieves significantly higher crushing resistance and lower open porosity compared to conventional expanded perlite, offering improved mechanical and thermal performance in the final mortar formulations. The performance of the closed structure perlite was systematically evaluated to identify the optimum grade for use in the innovative mortars. The study examined both the granulometry of the raw perlite and the applied thermal treatment conditions, while assessing key material properties such as loose bulk density, skeletal density, water absorption, crushing resistance, content of adequately expanded grains, mean granulometry, and particle morphology. Through this evaluation, the optimal product was identified as the grade combining lower skeletal density, which enhances insulation, and higher crushing resistance, ensuring adequate durability during mixing and processing. This optimized perlite serves as a robust lightweight filler that significantly improves the performance and stability of the final mortar formulations. To introduce thermal energy storage capability into the mortars, a hybrid perlite incorporating PCMs was developed. The process begins with drying the commercial perlite and melting the PCM. The two components are then carefully mixed to ensure proper impregnation, followed by vacuum drying to stabilize the PCM within the perlite structure. The resulting perlite PCM composite is coated in a pelletizing mixer. This hybrid perlite offers both lightweight characteristics and integrated thermal storage functionality, making it a key component of the PCM-enhanced mortar designed for improved indoor comfort and energy performance. The hybrid perlite was thoroughly evaluated to ensure its suitability for mortar applications. The assessment included leakage tests, SEM microscopy, skeletal and loose bulk density measurements, and crushing resistance. These tests allowed us to understand both the stability of the encapsulated PCM and the mechanical robustness of the composite particles. From the examined grades, the optimal product was the one exhibiting minimal PCM leakage, lower density, and higher crushing resistance, ensuring both good thermal performance and sufficient durability during mortar mixing and application. The preparation of the innovative mortars follows a process similar to that of conventional mixtures, with one key adjustment: the lightweight aggregates are added at the final stage of mixing. This approach minimizes mixing time and prevents particle fragmentation. Both fresh and hardened properties were evaluated to ensure proper performance. These measurements allowed us to verify the workability, mechanical behavior, and insulating efficiency of the newly developed formulations. The innovative mortars were upscaled using NTUA's fully automated pilot production line. The facility includes 4 silos for solid raw materials and 2 tanks for liquids, with materials transported via conveyors and pumps. Raw materials are mixed in a twin-shaft mixer with a capacity of 500 L, producing up to 3 batches per day. The entire process is monitored and controlled through a central computer system, enabling precise regulation of each step and ensuring consistent quality of the produced mortars. The pilot unit allows real-time monitoring of moisture content, energy consumption, and temperature during production. It also serves to evaluate both fresh and hardened properties of the mortars, bridging the gap between laboratory and medium-scale production. Optimal formulations are tested here to validate lab results, providing confidence in upscaling to industrial production while maintaining performance and quality standards. In summary, this work focuses on the development of innovative lightweight mortars that enhance building envelope performance. Closed-structure perlite serves as a robust, low-density filler, while hybrid perlite incorporates PCMs to provide thermal energy storage and improve indoor comfort. All materials were validated through laboratory, medium-scale, and pilot production tests to ensure consistent quality and performance. These solutions offer clear benefits for green and energy-efficient buildings, reducing energy demand, improving comfort, and supporting sustainable construction practices. Overall, our approach demonstrates a complete pathway from material design to scalable production, bridging the gap between research and industrial application.
This section presents a circular, cement-free geopolymer panel developed by SETMA, contributing to low-carbon and resource-efficient building envelopes. SETMA believes in a future where the construction sector is greener, more efficient, and truly sustainable. Its vision is based on a commitment to developing new materials, processes, and components capable of reducing environmental impact throughout the entire building lifecycle. From raw material selection to production, installation, and end use, SETMA works to introduce solutions that improve the energy performance of buildings. This vision guides all their research and innovation efforts, aimed at contributing to the sustainable transformation of the built environment.
SETMA has solid technical expertise in the development of eco-sustainable materials and products, with particular focus on the use of aggregates and binders derived from industrial and agricultural waste, the development and optimization of alkali-activated materials, AAM, as low-impact alternatives to traditional cements, the development of lightweight and fiber-reinforced concretes for high-performance applications, concretes enhanced with phase-change materials, PCM, to optimize comfort and thermal stability. Thanks to the experience accumulated over the years, SETMA is able to control parameters such as rheology, workability, density, mechanical strength, durability, and insulation properties. The circular panel developed by SETMA in the E4I project is an innovative solution designed to reduce the environmental impact of construction and promote more sustainable buildings. Key benefits include significant CO2 emission reductions using low-impact alternative materials, efficient use of energy and resources throughout production, incorporation of bio-based and recyclable materials, improving environmental performance. This technology is fully aligned with the principles of the circular economy and offers a significant improvement in indoor comfort, contributing to healthier and higher-performing buildings. Why is the panel circular? The E4I panel stems from a fully circular approach, valorizing secondary resources and minimizing the use of raw materials. The technology is cement-free, based on binders developed from industrial byproducts and agricultural waste, reducing environmental impact and emissions associated with cement production. The integration of recycled aggregates allows primary resources to be replaced with materials derived from existing waste streams, offering a dual advantage. Valorization of waste, turning it into new resources. Reduction of the overall impact of the construction sector. This approach aligns with EU circular economy goals and supports the transition to more sustainable building materials.
The production process of the E4I panel follows a simple, scalable industrial workflow: preparation of materials, molding, demolding, and curing. The entire cycle has been designed to be compatible with existing production lines and scalable at an industrial level. Compared to the target performance reported in the project table, the developed panel shows notable performance and compositional features such as good thermal insulation, supporting building energy efficiency, low density, facilitating transport, handling, and installation, recycled content exceeding 75%, highlighting its strong sustainability and circularity potential. These features make the panel ideal for construction applications, especially energy retrofits and lightweight building solutions. The E4I panel can be installed on various types of substrates: concrete, wood, and masonry. Mounting options include adhesive installation and mechanical anchoring. Thanks to its low density, the panels are easy to handle and install, making them particularly suitable for external retrofit projects and sustainable renovation projects. We conclude by presenting the full-scale demonstration sites, where the panels developed by SETMA will be installed to validate their performance under real conditions. Lighthouse Demonstration Building, Sintif, Norway. Installation in a cold climate to demonstrate thermohygrometric performance, the contribution to improved indoor comfort, the reduction of energy demand. Demo site NTUA, Greece. Installation in a Mediterranean climate to validate the system's effectiveness under different environmental conditions and demonstrate its application versatility. The building sector remains one of the largest consumers of energy worldwide, making the improvement of the building envelope a key step toward green transition. Traditional insulation materials simply delay heat transfer; they do not actively manage energy or adapt to environmental conditions. This presentation introduces a multifunctional material that combines 3D printing, lightweight minerals, and thermal storage technology. This advanced composite enables new possibilities for energy-efficient, low-impact construction. Compared to commercial cladding systems, which typically offer insulation but no thermal storage, our solution provides 4 major advantages. Integrated thermal energy storage through phase change materials. Extremely low weight thanks to tailored lightweight aggregates. Complete geometric freedom enabled by 3D printing, and high circularity potential due to mineral-based and recyclable materials. To achieve these functionalities, a closed structure expanded perlite, a PCM-enhanced hybrid perlite and a composite filament were developed through the collaboration of National Technical University of Athens (NTUA), Foundation of Research and Technology (FORTH), and Advanced Materials Simulation (AMS). Our product is a modular 3D printed element consisting of a printed external shell filled with hybrid perlite. This requires the development of a new expanded perlite grade compatible with extrusion-based additive manufacturing. The perlite was integrated into a thermoplastic filament to produce a composite material suitable for printing the shell. NTUA and FORTH jointly designed and optimized this workflow to ensure both structural stability and low environmental impact. To enhance both thermal and mechanical performance of the filament, a closed structure expanded perlite, CSP, was developed. It was produced through a controlled, purpose-oriented manufacturing process. The raw perlite is first crushed, sieved, and then expanded in a vertical electric furnace equipped with 6 pairs of independently controlled heating resistances, allowing precise temperature, particle movement, and residence time management. Through optimized thermal treatment, we produced fillers with tailored size, porosity, and sphericity, properties that are essential for smooth 3D printer extrusion and stable composite performance. The performance of the closed structure perlite was systematically evaluated to identify the optimum grade for use in the 3D printing technology. The study examined both the granulometry of the raw perlite and the applied thermal treatment conditions, while assessing key material properties such as loose bulk density, skeletal density, content of adequately expanded grains, mean granulometry, and particle morphology. Through this evaluation, the optimal product was identified as the grade combining lower skeletal density and higher sphericity. Using the optimized expanded perlite, CSP, as filler, a composite filament was engineered to print the facade elements. The filament is based on PLA and incorporates expanded perlite, CSP, as well as photocatalytic nanoparticles such as titanium oxide and zinc oxide. These additions enhance both mechanical strength and photocatalytic activity, contributing to improved environmental performance of the facade, such as pollutant degradation and reduced surface aging. PLA, closed structure perlite, and photocatalytic nanoparticles were mixed to form a homogeneous nanocomposite feedstock. This mixture was processed in a high-temperature extruder to create a continuous cylindrical filament optimized in diameter, uniformity, and flexibility. Mechanical properties and photocatalytic performance were evaluated by printing standard dog bones, testing pollutant degradation, and assessing reusability. This ensured that the filament met both structural and environmental requirements for green building applications. A full evaluation was performed to validate the composite filament as a sustainable construction material. We examined physical and mechanical properties, particle dispersion, morphology, and printability. In addition, 3D printed items were tested upon the degradation of organic pollutants, e.g. pharmaceuticals, detergents etc. The results confirmed that the composite supports stable extrusion, low density, and robust performance. Key characteristics that enable reduced material consumption, lighter building components, and improved environmental performance. The geometry of the facade panel was optimized to maximize structural stability while minimizing material use, a critical factor for green building. The internal lattice was designed to distribute loads evenly and resist deformation. Different compartment configurations were analyzed, and diagonal reinforcements were added for improved shear resistance. Printing parameters such as nozzle diameter, cooling, and speed were fine-tuned to ensure high-dimensional stability, low warping, and consistent surface quality. After printing the shell, a suitable filling material was required. NTUA produced a hybrid perlite by combining commercial expanded perlite with phase change materials. This hybrid filler provides both insulation and thermal storage, supporting buildings in reducing peak loads and improving indoor comfort in a passive, energy-free way. To produce the hybrid perlite, commercial perlite was dried and mixed with molten PCM to ensure deep impregnation. After mixing, a vacuum drying step stabilized the PCM inside the pore structure. The composite was then combined with silica in a pelletizing system to enhance shape stability and handling. The hybrid perlite was extensively tested through leakage analysis, SEM microscopy and density measurements. These tests ensured that the PCM remains stable even under temperature cycling. An essential requirement for green building materials. A multi-scale thermal model of the 3D printed PCM panel was developed by AMS, incorporating a prior material homogenization step to characterize the hybrid perlite composite, which was then used as input for the full panel simulation to evaluate key indicators such as U-value, enthalpy, and PCM activation efficiency. After characterization, the shell was filled with the hybrid perlite and sealed with a printed lid. Side grooves were incorporated into the design for mechanical fastening to the wall, enhancing durability and facilitating disassembly or recycling. Depending on the configuration, the element functions either as a lightweight facade panel or as an internal battery wall, enabling passive thermal storage and enhanced comfort in green buildings. PLA perlite 3D printed samples were recycled and mixed virgin PLA. Their mechanical properties were tested following the ASTM D638-14 standard test method for tensile properties of plastics. Their thermal conductivity and effusivity was tested using an TCI thermal conductivity analyzer, Ctherm Technologies Limited, Canada, using the modified transient plane method. 3D printed samples based on 50% virgin and 50% recycled PLA perlite indicated reduced thermal conductivity and effusivity. The 100% virgin PLA, 100% recycled PLA, and 50% virgin 50% recycled PLA blends demonstrated the most favorable mechanical properties. To conclude, this 3D printed cladding system brings together all the essential features of next-generation green building materials. It offers high recyclability, allowing components to be disassembled and reprocessed at the end of their life. Through the integration of PCMs, it provides active energy storage, increasing thermal stability throughout the day. Its lightweight structure reduces both material consumption and installation impact. 3D printing enables design freedom, tailoring geometry and performance to each building. The panel delivers high thermal stability thanks to the hybrid perlite composition, and overall the system contributes to a low-carbon building envelope based on mineral, low-impact materials. Together, these benefits highlight the holistic contribution of the system to sustainable, energy-efficient construction. The building envelope is evolving rapidly as demands increase for healthier indoor environments, energy-efficient buildings, and durable exterior surfaces. Functional coatings, paints that deliver performance beyond aesthetics, are becoming essential tools in achieving these goals. This part of the course introduces two practical developments in the field of functional paints: antibacterial interior coatings and infrared reflective exterior coatings. Drawing on a collaborative work between three partners, we explore how material selection, particle engineering, formulation adjustments, and testing approaches lead to coatings with measurable added value. The partners are RISE Research Institutes of Sweden, YS Cypriot Catalysts and Kansai Alton. This part of the course emphasizes real industrial workflows, surface modification, dispersion processes, paint formulation, and performance evaluation. Helping professionals in the building sector understand how functional coatings are developed, validated, and prepared for large-scale use. In recent decades, functional coatings have become mainstream solutions rather than niche products. Beyond providing color and protection, coatings today contribute to healthier indoor spaces, reduced heating and cooling, longer-lasting facades, reduced microbial contamination, and overall energy efficiency of buildings. The development of functional coating systems requires coordinated activities across material science, chemistry, product and process engineering and performance evaluation. In this task, we focus on developing two functional paint systems: antibacterial interior paints using copper-doped titanium dioxide, IR-reflective exterior paints using thermoplastic microspheres. Indoor spaces host a wide range of microorganisms. High-touch areas, rooms with high humidity and poorly ventilated areas can accumulate bacteria that increase health risks. Antibacterial paints help mitigate contamination by reducing the survival of bacteria on surfaces and limiting growth between cleaning cycles. Antibacterial paints present a good way of supporting hygiene in homes, schools, hospitals, and public buildings. Titanium dioxide modified with metals is known for its photocatalytic and antimicrobial properties. In this project, copper-doped titanium dioxide was selected as the active ingredient because copper introduces additional antibacterial mechanisms that work even in environments with low light. Here, we introduce the basic idea of photocatalysis. A photocatalyst, usually a semiconductor, is a material that becomes active when illuminated and generates reactive species capable of breaking down pollutants or inactivating microorganisms. When light hits the surface of the photocatalyst, the material absorbs photons. If the light has enough energy, meaning that the irradiation source has energy equal or greater than the energy gap of the semiconductor, electrons inside the material become excited. Titanium dioxide is one of the most popular photocatalysts due to its chemical stability and its efficiency under UV irradiation. By doping titanium dioxide with copper, we enhance electron trapping and improve both photocatalytic and antimicrobial activity. Here we describe the preparation method for the copper-doped titanium dioxide photocatalyst. The process begins with dissolving the copper precursor in water to distribute copper ions uniformly. Titanium dioxide powder is then added, and the pH is adjusted to promote effective copper incorporation. The mixture is stirred at controlled temperature to ensure proper interaction between the components. After filtration, the powder is collected, dried, milled, and sieved to obtain a fine and homogeneous material. Each step ensures reproducibility and good photocatalytic performance. In this slide, we walk through the full evaluation process of the copper-doped titanium dioxide photocatalyst. We start with the scale-up preparation, where larger quantities of the material are produced under controlled conditions. Once the photocatalyst is ready, we assess its activity using the methylene blue degradation test. This involves exposing the dye solution to the photocatalyst and observing how quickly the blue color fades. During the reaction, we use UV-vis measurements to monitor the concentration of the dye in real time. The data collected helps us compare different batches and evaluate how efficiently each one performs. After that, we carry out a series of physicochemical characterization techniques, such as XRF, XRD, BET, and particle size analysis, to understand the composition, structure, and surface properties of the material. Next, the photocatalyst is incorporated into paint or coating formulations to test how it behaves in a practical application. Finally, we evaluate the antimicrobial activity of these coatings, checking whether the presence of the photocatalyst can effectively reduce bacterial growth. Together, these steps give us a complete picture of both the quality of the material and its performance in real-world conditions. Here, we look at how we evaluate both the structure and the performance of the copper-doped titanium dioxide photocatalyst. We start with structural analysis using XRD. This technique allows us to confirm that the titanium dioxide crystal structure has been successfully preserved after doping. Because the copper content is very low, approximately 0.1%, it falls below the detection limit of XRD, which means we cannot see clear copper peaks in the diffraction pattern. For that reason, we need another method to verify copper incorporation. To confirm the presence of copper, we use XRF elemental analysis. XRF directly measures the elemental composition of the sample, and it clearly detects and quantifies the copper loading. In this case, the measured value is very close to the theoretical 0.1%, confirming that the doping process was successful. Next, we evaluate the photocatalytic activity of the material. The catalyst is tested using a dye degradation experiment under visible light LED illumination. The light activates the dye molecules, while the photocatalyst generates reactive species that break them down. By using UV-vis spectrophotometry, we track the decrease in dye concentration over time. The results show consistent and excellent performance across different batches of copper-doped titanium dioxide. Overall, these evaluations confirm both the correct composition of the material and its strong photocatalytic activity. To verify the antibacterial function, we test the copper-doped titanium dioxide photocatalyst in commercial paints before incorporating it into actual paints of interest. After preparing the material at scale, the photocatalyst is mixed directly into a commercial emulsion paint to create a functional coating. We then evaluate its antimicrobial performance by testing how effectively the coated surfaces reduce bacterial viability. The results show a dramatic difference compared to the control paint. While the untreated coating allows full bacterial survival, the nano-enhanced paint achieves more than 99.9% reduction for both S. aureus and E. coli. These results demonstrate that incorporating the copper-doped titanium dioxide particles provides strong antibacterial properties, highlighting the potential of such coatings for real-life applications where improved hygiene and surface protection are needed. Functional particles rarely enter paint formulations directly. They must be stabilized to prevent sedimentation, agglomeration, or uneven distribution. We perform the critical step of transforming powders into stable aqueous dispersion. As a first step, we select the surfactant based on particle polarity, surface energy, and paint compatibility. In the second step, we break down the agglomerates by applying high-shear bead milling and ensure uniform particle distribution. After milling, we evaluate dispersion stability by particle size measurement that confirms appropriate fineness for paint incorporation. Bead milling is ideal for this step because it can break apart agglomerates and create a uniform particle distribution that is compatible with paint formulations. The main principle of bead milling is shearing force and impact generated by high-speed rotating beads. Inside the milling chamber, thousands of small beads, often glass, zirconia, or ceramic, are accelerated by a rapidly rotating agitator. As the dispersion flows continuously through the chamber, the particles are subjected to shear forces created by the movement of beads against each other and the agitator, impact forces when the beads collide with the agglomerates or particles, and hydrodynamic forces from the high-speed fluid motion. Together, these forces break down particle clusters, reduce particle size, and produce a uniform and stable dispersion. Importantly, bead milling makes it possible to reach high nanoparticle concentrations, up to 38%, while maintaining consistent particle size and dispersion quality. This capability offers a major advantage for applications that demand highly loaded formulations. The resulting dispersion ensures smooth integration of the copper-doped titanium dioxide into the final interior paint without compromising texture, viscosity, or appearance. The engineered dispersion is then incorporated into a water-based paint system at different loadings. Paint formulations are prepared with specific attention to critical parameters that influence stability, performance, and application properties. These include ensuring dispersion compatibility with existing binder systems, avoiding excessive viscosity or poor leveling, maintaining opacity, color stability, and scrub resistance, and preventing changes in drying time or film formation. The antibacterial activity of the produced paints is verified using the methylene blue degradation test. Results show effective antibacterial performance at the lowest tested concentration of the dispersions, 1%, increased bacterial reduction as concentration increased, although higher loads may not be necessary for most applications. As a takeaway, even low levels of copper-doped titanium dioxide provide meaningful antibacterial action, making commercial integration feasible without significant cost increases. The copper-doped titanium dioxide dispersion we have worked with provides several advantages in real-life applications. Copper doping of titanium dioxide provides long-lasting antibacterial surface activity and works in low-light environments. The titanium dioxide dispersion is compatible with common water-based interior paint formulations. It is also expected to be cost-effective as minimal loadings are sufficient to obtain the targeted function. The antibacterial paint produced presents a way of supporting hygiene in homes, schools, hospitals, and public buildings. High-touch interior surfaces in residential spaces can be protected with such antibacterial paints. Dark facades tend to absorb significant heat, leading to higher cooling loads and faster paint degradation. Therefore, solar reflectance plays a major role in regulating building temperature, especially in sunny climates. Traditional dark coatings absorb heat, which leads to higher cooling loads, surface overheating, and faster paint degradation. IR reflective paints address these challenges by using pigments that reflect infrared radiation while preserving the desired visible color. By reducing surface temperatures, these coatings improve energy efficiency, extend facade durability, and support growing market demands for sustainable, thermally efficient building solutions. IR reflective paints reflect a greater portion of solar radiation, particularly near-infrared wavelengths. One emerging additive to acquire solar reflectance is thermoplastic microspheres that expand into hollow spheres when heated. These hollow structures improve optical scattering, surface reflectivity, and insulation properties, contributing to energy-efficient building exteriors. IR reflective paints are developed by selecting suitable thermoplastic microspheres containing encapsulated gases, incorporating them into exterior paint at varying concentrations, controlling film formation to preserve the hollow structure, measuring total solar reflectance, TSR, and comparing performance across formulations. Microsphere expansion produces a low-density microstructure, air-filled cavities with strong scattering ability, and increased reflectivity across visible and IR wavelengths. As can be seen in this graph, higher microsphere loadings generally improve TSR, but optimal levels depend on mechanical properties and film durability. In this case, the optimal level has been 15% loading of microspheres. This collaborative work demonstrates how combining material innovation, dispersion engineering, and industrial formulation leads to functional paints with real impact in the built environment. Copper-doped titanium dioxide yields effective antibacterial interior paints with minimal additive loading and straightforward production integration. And thermoplastic microspheres enable IR reflective exterior coatings that improve energy performance and surface durability. Together, these case studies show how functional coatings can be systematically developed from raw materials to validated performance, supporting healthier, more energy-efficient, and more durable buildings. This section is about the photovoltaic thermal modules integrated and applied in buildings. In the Exploit 4 Innomat project, Solitec, Cintiq, and University of Stuttgart combined the technical expertise to develop innovative private solution for integration into buildings. Private technology brings together solar electrical power generation and heat production in one system, making better use of available roof space or be mounted on the facade. This hybrid approach offers a practical way to supply both electricity and useful thermal energy for everyday applications. Private modules consist of PV module and thermal absorbers with high thermal conductivity and high efficiency of heat exchanger. As private modules heat up by solar irradiance during normal operation, the circulating liquid inside the thermal absorber heat exchanger draws this heat away. The increase of the working fluid temperature becomes the thermal energy output, can be used for household needs such as heating water or supporting a heat pump. In addition, it is a mutually beneficial process, where the PV modules run cooler and generate electrical power more efficiently. The target of private properties in Exploit 4 Innomat project are listed below. The private itself should be lightweight and should have the thickness no more than 30 mm. The target power capacity is 500 watt per square meters. Durability and reliability aspects should comply to standards typical for PV products. In addition, the thermal absorber component should use lightweight materials with density below 3 gcm3, have good thermal conductivity, able to generate required thermal energy output, while having homogeneous flow velocity within the pipes of the thermal absorber. From now, the design and manufacture of private will be presented. As schematically shown in this figure, the new private product to be produced has the following materials component composition: glass layer, POE encapsulate, solar PV cells, POE encapsulate, glass layer, bonding or glue materials, thermal absorber and heat exchanger component. The whole process consists of 1. Design, development and manufacturing of the thermal absorber component. 2. Assembling and manufacturing of private products. 3. Testing and demonstration of the possible integration of private to the concrete elements. For the thermal absorber, aluminium alloy tubes with multiple channels have been selected as the main component. The 3D design was made in the SolidWorks software, and later fluid flow and heat transfer inside the thermal absorber was numerical simulated using finite element software. Here is an example showing the flow distribution in meters per second inside the thermal absorber. Besides, the numerical simulation could predict the temperature of the fluid at the outlet, which then could be used for evaluate the thermal energy output. The influence of different geometrical designs and the inlet flow rate could be studied as well. Considering the assembling process, for example, a bonding that needs heating up and then a subsequent cooling process. This process could be simulated by numerical simulation of the structure mechanics. Here shows the von Mises stress of the two thermal absorber after assembling process. One without gap in the bonding surface of aluminium thermal absorber, while the other has gaps. The simulation results clearly show that introducing gaps in the thermal absorber could reduce the thermal stress, which is beneficial for the assembling or manufacturing process of private. Afterwards, aluminium thermal absorbers have been manufactured by joining technologies that manifolds, many tubes been joined together. The next step is the development of the assembling process of private, which is mainly about bonding the aluminium thermal absorber with the glass layer of PV. For such purpose, first small test samples with 300 by 50 mm dimensions have been produced and then bonded together with 50 x 50 mm bonding area. Such small-size test samples are tested in tensile or stretching machine to determine the adhesion strength. In addition, the small-size test samples could be placed inside the climate chamber for durability test. The bonding strength using polymer is 5,807 Newton per 50 meters, and using glue is 4,823 Newton per 50 meters, which are enough to hold the PV part. The private process is semi-manual, but with additional equipment related to glue dispensing and mechanical pressure it can be automatized. The process of assembly starts with the surface preparation of PV module by cleaning with isopropyl alcohol and drying. In parallel, the mixture of two-component glue is prepared, by mixing 1:1 and stirring all together. Then, the deposition of glue follows where around 2.5 liters per private module is used. The mixture is distributed evenly on the back surface of private and then heat exchanger is placed on top of the backside with applied glue layer. For the final step, external load is applied on top of the heat exchanger for more efficient curing process. With such assembly process, certain amounts of PVTs have been produced, and an example is shown here. After production of the private, several characterizations have been performed. Due to simplified design of heat exchanger, private module electrical properties have been characterized before the gluing process. The application of glue and heat exchanger does not impact the insulation properties of the private module. The current and voltage measurements of produced private modules showed no deviations from expected and predefined values. The electroluminescence procedure for PVTs confirmed the reliability of previous measurements and showed no electrical failures. Insulation resistance test showed good results as well, which fulfills the insulation resistance requirement according to the standard. In addition, the mounting or integration option of private to the concrete elements have been tested and demonstrated. Here one option is presented. Aluminium L profiles were accurately and directly welded to the rear of the private panel's heat absorption and exchanger unit. The concrete element was mounted using Fisher AE2 M10 dowels, then M10 stainless steel screws and washers were inserted through the aluminium L profile flanges and tightened to an exact torque level. These figures show the mounting integration of one private module to the concrete that commonly be a facade elements. The resulting connection system offers mechanical robustness and resilience against environmental exposure. Finally, we would like to give a short summary about the private products that we developed and produced in this project. In this course, we have introduced the private, including its properties, design, manufacture production, and their integration in building. Further demonstration and testing of their real performance will be realized in different lighthouses. Green building strategies aim to reduce environmental impact, optimize resource efficiency, and enhance occupant well-being. Achieving these goals requires the integration of innovative materials that combine performance, sustainability, and adaptability, paving the way for next-generation construction solutions. Thank you for your participation and for completing the course, A Roadmap for Sustainability and Decarbonization of Buildings. Role of Exploit for Inamat.